Dear students, after studying this module, you shall be able to understand what are SE2 reactions. You shall be able to learn the mechanism of SE2 reactions and identify the type of SE2 reactions based on stereochemistry of the products. You shall also be able to evaluate the conditions which will favor the SE2 reactions, and after going through all these you shall be able to analyze the importance of organomercury compounds in SE2 mechanism. So, let us begin with knowing what are SE2 reactions. Electrophilic aliphatic substitution reactions, as you are aware, are the chemical reactions in which an electrophile, which is an electron deficient species, removes a functional group in a compound. That is, there is overall a substitution where the electrophile is attacking and replacing that group or atom. The electrophilic substitution bimolecular mechanism are termed as SE2 mechanism. So, here you can notice the 2 stands for bimolecular, E stands for electrophilic and S stands for the substitution. And just analogous to SN2 reactions, these reactions follow the bimolecular rate kinetics, where the reaction rate is first order in the substrate and first order in the electrophile when both the reactants are in dilute solution. Now, going into more details about the SE2 reactions. The SE2 reactions involve a substrate with good leaving group and an electron deficient electrophile. When we say good leaving groups for electrophilic substitution are those which have outer shell that is deficient in a pair of electrons. And furthermore, they are too much electron deficient more, and that is enhanced if you have more electronegativity of the atom involved and electron withdrawing group further attached. The proton is a common leaving group in aliphatic systems, especially the acidic protons, such as protons at alpha position to the carbonyl group or at an alkynyl position. Going further, organometallic compounds are also especially susceptible to these electrophilic substitution. So, we shall be going into details of all these. So, let us try to understand the mechanism of SE2 reactions before we take further more examples and where it happens and how the stereochemistry is involved. The SE2 reaction mechanism proceeds via a single transition state where the old bonds and the newly formed bonds are both present simultaneously. That is, the old bonds are in the process of breaking and the new bonds are in the process of breaking, and both these are happening simultaneously. Unlike the SN2 substitution, which always result in inversion of configuration of reaction center, note that for SE2 reactions there are 2 possible ways of electrophilic attack to the reaction center. The first one is the attack from front, and this is called as SE2 front, and this results in the retention of configuration. As you can see here, shown is the SE2 front, and here you can see that it is the Y plus which is the electrophile, and these electrons will be moving here to form the new bond between C and Y, and as a result the Z will go out as the leaving group, so it goes out as Z plus. So, this is how the SE2, and you can notice the attack of Y plus is from the same side as the leaving group Z is there, and that is why there is a retention in configuration which will be happening. The second option is the attack of electrophile from the rear or the back side, and this is called as SE2 back, and this leads to inversion of configuration, and this is analogous to the SN2 attack. So, you can see here that Y plus is the electrophile which is attacking from the back side, opposite to that the leaving group Z is there, and then these electrons will form the bond between Y and C, and eventually the Z goes out as Z plus. So, this is the SE2 Beck mechanism that you can see here. Moving further, after this, knowing that there are two types of these mechanisms, majority of second order electrophilic substances proceed via retention of configuration, and this implicates that the front type attack is more common, that is, it is resulting from the SE2 front mechanism. For example, as you can see here, from this particular equation, this compound 1 which was treated with labeled mercuric chloride, the product 2 which is produced is there with 100% retention of configuration, and thereby out of the SE2 back and SE2 front mechanism, it clearly implicates that it is going through the SE2 front mechanism. So, you can notice that in this equation that this particular part of the group is getting replaced by the HgCl. So, you can see the Hg, the labeled one is getting incorporated, and it is not that the initial present Hg is there in the product. So, this is clearly indicating that how this change is happening, and that is also with the retention in stereochemistry. For an electrophilic substitution reaction, evidences for front attack are second order kinetics along with stereochemical retention of configuration. SE2 front reactions are possible and easy at bridgehead carbons. Further, even the bulky substrates such as neopentyl systems undergo electrophilic substitution, although the SN2 reactions at neopentyl and bridgehead positions are extremely slow, and this is because the attack from the rear is blocked because of the cyclic ring present, and the transition state for the reaction lies very high in energy. Talking about SE2 back reactions, they proceed with inversion of configuration as is evident by their mechanism. The reaction of optically active secondary butyl trineopentyl tin as shown here when is reacted with bromine gives the inverted secondary butyl bromide. So, this is an example of SE2 back reaction, and that is why the inversion can be justified. Now, going into the details of stereochemistry of SE2 reaction. In the SE2 mechanism, in the transition state, the two electrons of the carbon metal bond occupy the central orbital, and it was proposed by Ingold et al. That the electronic distribution giving rise to different stereochemistry of products depend on the degree of bond extension and the degree of bond ionicity of the intermediate in the transition state. If we consider the SE2 back reactions, it was shown that the transition state has good bond extension potential and high ionicity. Thus, the carbon orbital spreads comparably on both sides of the atom, leading to the inversion of configuration. In contrast, the transition state has little bond extension and low ionicity. The electrons of the original metal bond remain nearly where they were, resulting into the retention of configuration through a transition state such as SE2 front, as you can see here. So, this SE2 front will be giving you the retention in configuration, but on the other hand you can see in this visual the SE2 back will give you the inversion in configuration. In a classical experiment to determine the stereochemistry of SE2 mechanism, secondary butyl mercuric bromide was reacted with racemic secondary butyl magnesium bromide, leading to the optically active product disecondary butyl mercury having one secondary butyl group optically active and the other with the racemic center, that is L is obtained. The disecondary butyl compound was then further reacted with mercuric bromide to give two equivalents of secondary butyl mercuric bromide. The steric course of the reaction was predicted assuming that the bonds between mercury and each carbon has a 50% chance of breaking. So, there were three possible outcomes from this reaction, and let us discuss them one by one, that is A, B and C. Let us discuss the case A. If inversion is going to happen, then what you can see is this in R HgR, if the attack happens between the R and Hg bond, that is the R stereochemistry of this R component will go into S, but the RS stereochemistry of this R will remain RS. If the attack happens alternatively between this Hg and R, then in that case the R remains R and RS remains RS. So, if you see, the sum will be a racemic mixture, that is from top we are getting this R and here it is R. So, it will be eventually the racemic mixture. If there is retention, then this is the case B. So, what you can see here is in this first molecule, the RHgR, if the attack happens here, the R remains R because of retention and RS remains RS. So, we get mixture of these two products, and alternatively if the attack happens here, then again the R remains R and RS is retained RS, and the sum will have 1/2 of the original activity. If we consider the case C, that is racemization, then the attack happening here is giving you RS and this component giving you RS, that is you get RS and RS. Similarly, if the attack alternately happens here, then again we are getting R plus RS. So, the sum has 1/4 of the original activity. So, here you can notice that R is this isobutyl group, and the reaction resulted in the product with 1/2 of the original optically activity, which is indicated by the B case, that is pathway B, therefore demonstrating the retention of configuration under the several different set of conditions. So, thus retention of configuration suggested that there is the SE2 front mechanism which is operating for this reaction. Now, after this, if we try to look at the factors influencing the SE2 reactions, which we will be discussing in detail in the subsequent modules, but here let us look at a brief view. First of all, it will be dependent on substrate, then the leaving group and the solvent. So, considering the case of substrate, for the SE2 Beck mechanism, the reactivity of alkyl groups is methyl is more than ethyl, propyl, isopropyl and neopentyl. So, as it is expected, since the backside attack is significantly affected by the steric hindrance, so you can notice that as we are moving from methyl to the neopentyl, the bulkiness is increasing and hence the reactivity is decreasing from methyl to neopentyl. There are strong effects of substrate structure on kinetics of SE2 front mechanism. For the reaction as shown here, that is RHgBr plus bromine, formation of RBr and HgBr2, you can see that this reaction is catalyzed by bromide ion and this is going via the SE2 front mechanism. And you can see in this table shown that there is a relative data which has been given where the variant is different alkyl substituent. So, you can see the relative rate when it is methyl it is 1, it is ethyl it is 10.8. Further as we go higher, this relative rate you can see it is varying. And as can be seen from the table, the branching at alpha carbon increase the rate of reaction due to the electron donating inductive effect of R groups, which will stabilize the electron deficient transition state in the SE2 front mechanism. But on the other hand, the branching at beta carbon decrease the reaction rate significantly due to the steric hindrance. So, you can notice that from methyl to this particular case where it is tertiary the rate is increasing, it is increasing from 1 to 3370. But on the other hand, when we are having the bulkiness at the beta carbon is higher, then the rate is decreasing and it is going to almost 0.173 in this last case. In contrast, some organotin substrate, the rates of second order substituents were found to increase with increasing electron withdrawal by substituents, and this was explained based on the associated ion pair to an SE2 mechanism analogous to the Sneen's ion pair mechanism for the nucleophilic substituent. SE2 front reactions are possible at sterically crowded positions such as a bridgehead carbon or a neopentyl system owing to the orientation of incoming electrophile. So, you can see that there is no backside attack because of these rings possible, and similarly the groups in neopentyl which are providing the steric hindrance. So, there will be only the front side attack. So, that is how the nature of substrate will be affecting. Moving to the nature of leaving group, electrophilic substitution requires an electropositive leaving group attached to the alkyl group substrate, and in aliphatic organic chemistry most of the functional groups are electronegative. Therefore, due to the lack of substrates, the number of electrophilic substitution reactions is less as compared to the nucleophilic substitution reactions. Generally, the SE2 reactions proceed with alkyl groups attached to metals as leaving groups. Organomercury compounds have been most extensively studied for the SE2 reactions as they are stable and sufficiently reactive, easily prepared, purified and identified. For the substrate RHGX, the more electronegative group X decreases the polarity of C-Hg bond and results in less stable HgX plus. Therefore, the leaving tendency of HgX decreases with the increasing electronegativity of X. Thus, we can say that HgR from RHgR is a better leaving group than the HgCl which is from RHgCl. Coming to the effect of solvent, there are considerable effects of nature of solvent on SE2 reactions. When competing SE1 and SE2 reactions may run parallel, then polar solvents will favor the SE1 mechanism, while the less polar solvents will favor the SE2 mechanism. If we look at comparison between the SE1 and SE2 mechanism based on reactivity, then SE1 mechanisms are favored in comparison to SE2 if there are strong electron withdrawings, that is -I group present on the substrate alkyl group, or the polar plotting solvents are used for the reaction. Now, after studying about the mechanism of SE2 and knowing what is SE2, let us consider some examples of SE2 reactions. First is the alkyl exchange. The rate of this reaction as shown here, that is RHGX plus HGX2, where Hg is labeled in the presence of ethanol giving RHGX plus HGX2. So, the rate of this reaction where the alkyl exchange is happening with alkyl mercury substrate was found to follow the second order kinetics with the retention in configuration. So, therefore, it implicates that it is the SE2 mechanism, and because of retention it is the SE2 front mechanism. Furthermore, support for SE2 mechanism was provided by the rate coefficient that increase in the order of x equal to Br will be less, I becomes more, higher in rate than OAC than NO3, and this is again predicting the FC2 front mechanism. Another example by the use of radioactive mercury is as shown here. So, you can see that this particular molecule where this Hg is labeled is reacting with this in the presence of ammonia, then this is how there is a coupling of these two happening, and this is again the SE2 mechanism which is there. Considering the deuteration reactions are important from the mechanistic point of view. Such reactions with alkanes are accompanied by treatment with superacids like HSO3F or HFSBF5, and this is done because strong acids can only remove slightly acidic protons. So, this RH when it is reacted with D plus then it will be going into deuterium exchange, that is H is getting replaced with this deuterium. The mechanism of exchange involves attack of H plus or D plus on the CH bond to give the pentavalent methanonium ion as shown here when the reaction is carried out in methane. So, you can see this when methane is reacted with DF SBF5, then you will be getting this pentavalent intermediate, and further it will dissociate into the labeled CH3D. You can see this is the labeled methane that you have obtained, and it can also go into the unlabeled one. These reactions are SE2 reactions, as both the entering group and the leaving group are electrophilic in nature, and in the transition state the electron pair of the breaking bond remains with the substrate. The next example we can consider is the halo-demercuration. The reaction of benzyl mercury halides with iodine in the presence of an excess of cadmium iodide was found to be the second order overall and first with respect to each of the components, and this was done in various solvents like methanol, ethanol, dimethyl formamide. So, you can look at this reaction where this HgX is getting replaced by I. The next example we can consider is the proto-demercuration. The reaction of benzyl mercury chloride with hydrogen chloride in alcohol as shown here and in the presence of dioxane was found to follow the SE2 mechanism. The substitution of 1-cyano-1-carbethoxypentyl triphenylphosphine gold 1 by alkyl mercury salts was found to follow SE2 mechanism, and this reaction you can see is depicted here. So, here again this particular group is getting substituted with RHG, and this is the SE2 mechanism. Another reaction you can consider is this one where R4SN is reacted with HgX2, where we get a RHgX and R3SX, and this also follows the second order kinetics. The next example we can consider are the bimolecular allylic rearrangements, which are referred to as SE2 reactions. Allylic organometallic compounds may undergo electrophilic substitution reaction at the alpha or gamma carbon atom. If the attack is on the gamma carbon atom, then the reaction is referred to as SE2 that is bimolecular electrophilic substitution reaction with rearrangement. In SE2 is representing the rearrangement, and the general scheme of the reaction you can see is shown here, where this allylic alkene bond is attacking on the electrophile, and in turn this MXN will get removed and the double bond is created between these two carbons. So, there is a rearrangement which is happening via this electrophilic substitution is taking place. For example, the allyl silanes, this reaction as shown here proceeds even when the allylic group has a bulky substituent attached to it. The product of rearrangement has been shown to have anti-conformation of allyl silanes with a very high degree of stereospecificity, that is around 95%. So, as you can see here, starting from this methyl silane at the allylic position, and we are taking this almost in 99.9% enantiomeric excess, the pure form, and when this is reacted with this bulky electrophile, what you get is that this is coming at this position, and you can notice the double bond is going at the rearranged position, and you can clearly see that there is high degree of stereospecificity which is there in this reaction which is happening via the rearrangement. Moving further, most electrophilic allylic rearrangements involve the loss of hydrogen, but they have also been observed with metal leaving groups, and an example of this we can see as shown here. This is proceeding with the acetic acid perchloric acid functional by an SE2 mechanism, and you can clearly see here that how this is undergoing rearrangement, and there is a loss of this metal component which is Hg as HgBr which is going out. Another example of SE2 reaction with allyl magnesium substrate giving rise to rearrangement product is as shown here. You can notice that this substituted acetophenone when is reacted with this allyl having MgCl at the allylic position, then what we get is this intermediate product which further on hydrolysis will give this alcohol. So, here again you can notice that there is a rearrangement which is happening. Let us now summarize what we have learnt in this module. We have learnt that electrophilic substitution bimolecular reactions referred to as SE2 are the ones where an electrophile, that is electron deficient species, replaces another group in the substrate. SE2 reactions proceed via a single transition state where concerted bond formation and bond breaking takes place. SE2 reactions are further divided as SE2 front and SE2 back, and that is based on the direction of incoming electrophile, which also decides the stereochemistry of the products. For the SE2 front mechanism, reaction proceed with retention in configuration because it is attacking from the same side as the leaving group, whereas the SE2 back mechanism will generally give rise to the racemic mixture that we have already discussed. The SE2 mechanisms are rare due to the requirement of an electrophilic leaving group, which is rare in the aliphatic organic compounds. SE2 mechanisms are favored by less polar solvents, and SE2 mechanisms may take place also at the bridgehead carbons and bulky neopentyl groups via the SE2 front mechanism.